right, so today we're going to wrap up Chapter 2 with Section 2.10 on negating statements. We've seen a couple of cases where we negated a statement. In particular, we have De Morgan's laws. They tell us, basically you can summarize De Morgan's laws is that if you take the negation of an and statement, you'll get an or statement. If you take the negation of an or statement, you should get an and statement. Okay, so you have those. So some other things to consider in 2.10. So the negation of P, I mean, that's what it's called. This is called the negation of P. And if we say statements, we define statements as sentences that are either always true or always false, then when you're looking at a statement and you say, oh, this statement is false, well then its negation has to be true. So, and vice versa. So it can be useful to know what it actually means, what the exact meaning of the negation of a sentence, of a statement. And some of these statements will be kind of complex. So, for example, here's an example. So here's the statement. X and Y are odd. Okay. So one of the reasons why we study logic is that if we can translate statements into logic, then we're going to know exactly what the sentence means, and we can do things like take the negation of it, and we know exactly what we mean. Okay, so X and Y are odd. So this is an and statement. If you think about it, let me rewrite this as kind of like in symbolic notation. We're saying X is odd, and Y is odd. Okay. Right? So if I negate this, negate an and statement, I should get an or statement. So you remember De Morgan's law? It says, say I want to take the negation of this sentence. So I'm taking the negation of this and statement. What De Morgan's law says, if I negate P and Q, I get the negation of P or the negation of Q. So the negation of the sentence X and Y are odd is it is not the case that X is odd, or it is not the case that Y is odd. Well, what's a better way to say it is not the case that X is odd? Yeah, let's just say, how about that? X is even, or Y is even. So isn't that a better way to, it's an easy way. So that's the opposite, that's the negation of the sentence X and Y are odd. The negation of X and Y are odd is the sentence X is even or Y is even.
So how would you say that X is even or Y is even, but not both?
Well, they both could be even. The or means one or the other or both. So it's like, the negation of an and statement is an or statement, and so it could be the case that X and Y are both even. Okay. X is even or Y is even, or both. So is the sentence, would you say X or Y is even? If you translate it back into like English, is that the proper English? X or Y is even?
You have to have both in there, wouldn't you?
No, that's the opposite of. So these statements are all. So the negation of X and Y are even is the same as saying that X or Y. Sorry, the negation of X and Y are odd is the same as saying X or Y is even. Right. So it's not X or Y are even, right? It's X or Y is even. Yeah, My math has always been gooder than my English, but I'm pretty sure it's an is. Okay, any questions? No? All right. Let me do another example right here. How about this? Here's a sentence. Every integer is prime. Believe that statement? No. It's false, right? So the negation of it should be a true statement. So let's talk about the negation of this sentence. The negation, well, how about we write this in symbolic notation first? How would you write every integer is prime in symbolic notation? Yeah, you have an every, so every integer is n and z, right? So that's the phrase, that's how you translate, usually I translate every integer. Right? Okay, so every n and z. Well, what about n? N is prime, right? Okay, make sense? All right, so we all agree that this is a false statement. So every integer is prime. It's false. So the negation must be true, right? So let's look at the negation now of the sentence. The negation of this. This must be a true statement. So what does it? Yeah, what does it mean that it's not the case that every integer is prime? There exists an integer that's not prime?
That's what
Did we say? You said something else.
I was going to say there exists an integer that isn't prime.
There exists an integer that isn't prime? Does it make sense? Is that the same as saying it is not the case that every integer is prime? If it's not the case that every integer is prime, you're right. There has to be at least one integer that's not prime. So those are saying the same thing. So it is true that and if I said it is not the case that every integer is prime, I'm really saying something about some integers, or at least one. There should be some integer that is not prime. So if there exists an integer n, such that it is not the case that n is prime. So remember, De Morgan's law, when you distribute this negation of an and, it switches it to an or. So the negation kind of, when you distribute it, it kind of toggles between and or. What we're going to see is that it toggles between the two quantifiers as well. When you move this negation symbol in, it's going to change the quantifier. It's going to switch the quantifier. If it's a for every, it's going to switch to there exists. If it was a there exists, it's going to switch it to for every.
So if all goes to at least one.
There exists, or depending on the sentence, one of those phrases will be better than the other. Will just sound better. But there exists. So you have the universal and then the existential quantifier. They switch. So if I saw this sentence, how would I rewrite that in English? I wouldn't say there exists an integer n such that it is not the case that n is prime. I mean, that's a literal translation, but what are we trying to say? Okay. Yeah. That's kind of this one. Not every integer is prime. That's one way of saying it. But this is saying some integer is not prime. Yeah. Like you put out. So are every integer either composite or prime? We know that every integer is either even or odd. The number 1 messes it up because 1 is not prime and 1 is not composite. But yeah, you're on the right track. So that's the idea, right? So in this case, I would still stick with the phrasing not prime. So I would say, how about some integers are not prime? Okay, that's one way to say it, but there's many other ways. Somebody said like not all integers are prime. That's kind of like this. But that's the same. If I said not all integers are prime, that's the same as saying some integers are not prime. Okay, or there exists an integer that is not prime. There exists an integer n, such that n is not prime. I mean, if you want to do a literal translation, you can, but this is probably a better way to say it. Any questions so far? So the negation of an and statement turns out to be, if you take this negation inside, it switches the quantifier. We'll do another example of that.
I was gonna ask that.
Yeah.
Is like the negation of like a set, would it just be the set's complement?
Well, if saying if saying X is not in a set, is the same as saying X is in the complement of that set. But you can't take the negation of a set, right? You can take the negation of a sentence. So if I said it's not the case that X is in S, that's the same as saying that X is in the complement of S. As long you have like you understand what the universal set is. Okay, here's another example. Here's a there exists statement. How would you read this sentence? Or what's the meaning of this sentence? You know, instead of thinking of literal translation. You know, the literal translation. What is this?
There's a real X.
There's a real number X. There exists a real number X such that X squared equals -1. Okay, you say something like that, like. And if you think about it long, you might recognize it. You might say something like. The square of some real number is -1 or something. I don't know. You can start off with there's some real number X such that X squared equals -1. Okay. How about so the way I would kind of think of this is there's a real number whose square equals -1. I mean, in real world English, people don't usually define variables in their real book sentences. So you often find the sentences that the book might use as like more English. They don't have variables like n or z or x. Okay, so let's take. There's a real number whose square equals -1. Is that true or false? False. It's false. There is a number whose square is -1, but it's not real. It's an imaginary number or a complex number. So this is a false statement. So let's take the negation of this. So the negation okay. So if you negated this sentence, I mean, if I said there is a real number whose square equals -1, you just say there does not exist a real number, or there is no real number whose square equals -1. There is no real number whose square is -1. So if I'm saying there does not exist a real number with some characteristic, I'm really making a statement about all real numbers. I'm saying there's no real number that has some characteristic. So that's really a universal statement about all real numbers. So the negation of this there exists statement is actually equivalent to a statement about all real numbers. For any real number x, it is not the case that x squared equals -1. Those are actually equivalent statements.
Could you also say for all x that are not elements of real numbers, x squared is equal to -1?
No. That's not what we're saying here. Because the square of every complex number is not -1. So if this statement is false, then negation has to be a true statement. So what you just said is not a true statement, so they can't be equivalent. So for every real number x, it is not the case that x squared equals -1. Or the negation of an equation, you could just say not equal to. You could also say something like this, like for every real number x squared does not equal -1. Maybe it's slightly simpler notation. So I could just say something like the square of every real number does not equal -1. Or no, there's no, you're saying there's no real number whose square equals -1. It's the same as saying the square of every real number does not equal -1. Okay. Like that. square of every real number. Oh, how about n? How about that? The square of any real number does not equal -1. So those are negation, those senses are negations of each other. There is a real number whose square equals -1. Actually, the square of any real number does not equal -1. This is the negation of that. Okay, any questions so far? So let me kind of summarize this idea of, this is, I'm going to call this a fact, that the negation of a for all statement, so I say have for all x in some set or whatever, and then some statement about x, okay? For every x, p of x, okay? I'm taking the negation of a for all statement, that is equivalent to there exists an x such that it is not the case p of x. So if I bring the negation inside past the quantifier, it's going to switch to the quantifier. And then the same thing is true for if I said it is not the case that there exists an x such that p of x. That's the same as saying for every x, it is not the case that p of x. Okay. So when the negation symbol moves past the quantifier, it toggles the quantifier, switches the quantifier from
So if we
one
have
to the other.
like, or there's a y for every x, then it would become for every y there's an x.
Yeah, and I'll do an example of that too. If you have back-to-back quantifiers, once you go past both of them, you switch both of them. Yeah. Okay. Let's do it. I have to do an example next. Two quantifiers. Okay. Okay, so I think we may have looked at this statement already before when we combining quantifiers. Let's look at this. So it says there exists an integer x such that for every single y, for every integer y, we have that x plus y equals 0. Okay? Or another way you kind of translate it, there exists an integer x such that x plus y equals 0 no matter what integer y you give me. True or false? So can you find an integer, okay, x, that no matter what y you put here, the sum's always going to equal 0?
False.
It's false. What we're saying is there exists an x that works for every other integer that you choose. There's an x that if you add it to any other integer, you always get 0. That's not true. If I reverse this, so if I said for every integer x, I can find a y, there exists a y, such that x plus y equals 0. That's a true statement. But this one's false. Okay? There's no x that I can add to any other integer to equal 0. Okay. So if this is false, then the true statement would be the negation of this. Okay, so this one has to be true. Let's see if I can rewrite this. So if I bring this negation sign in, I'm going to get, off next here. So it's not the case that there exists an integer x. So for every integer x, same thing, I'm bringing this past this quantifier and put it on the inside. I'm going to change this to, so for every integer x, there exists an integer y such that it is not the case that x plus y equals 0. Okay? So if you bring the quantifier past both, if you bring the negation sign past both quantifiers, you have to switch both quantifiers. So this became for every, after it became that there exists. Let me rewrite this one more time. For every integer x, there exists an integer y such that x plus y does not equal 0. So, right, the negation of x plus y equals 0 is the same as x plus y does not equal 0. So this should be true. Let's convince ourselves this is true. For every integer x, okay? So no matter which x you start with, any integer, start with any integer, I can find there exists a y such that x plus y does not equal 0. You believe that? It's true. So no matter what x you give me, I can find a y so that the sum does not equal 0. Okay? All right. No, we didn't have a break today, but we might have gone down to the vending machine down there and got a little snack cake or something, and maybe that snack cake was made by the Sara Lee company. You guys heard of Sara Lee? Snack cakes and different kinds of cooking things. Okay, so there's a point to this. So Sara Lee used to have a slogan that involves complicated negations. Their slogan used to be, everybody doesn't like something, but nobody doesn't like Sara Lee. So do you think there's an easier way to say that that's equivalent? You maybe have heard this jingle. It's actually, they changed their slogan in 2006. So if it used to be, before 2006, there's this little jingle that went with it. Nobody doesn't like Sara Lee. I don't know if anybody, you guys remember that? You remember that? You remember that?
I've heard it before.
Yeah, so they don't use this anymore. Now their slogan is boring. It's the joy of eating. But, that's not going to help me in my street class. So I'm going to use, so let's think about this. Everybody doesn't like something. So there's two quantifiers here. There's an every and there's a sum. So this is like a two quantifier statement. All right, so I'm gonna rewrite this symbolically. U is going to be the universe of all people. V, that'll be the universe of all things. In this sentence, everybody doesn't like something. So how would you say everybody? For all, and then I take an arbitrary element of U. So I'm going to call that, I'm going to say X. Okay? For every X in U, that's for every person, for everybody. All right. Everybody doesn't like something. There's something that exists that this person doesn't like. So for every person, there exists something, there exists some Y and V. So for every person, X, there exists a thing Y, such that it is not the case that X likes Y. What do you think? For every person X, there exists a thing Y such that it's not the case that X likes Y. So everybody doesn't like something. So think about what we know about quantifiers. What if I took this negation and moved it back out? How could I also say this slogan? So if I move this back out, I got to do the, I got to switch these quantifiers. So there exists a person such that for everything Y, X likes Y.
You put the negation sign out in front of that?
So yeah, these statements are equivalent. So this statement equals this one. So I took the negation, instead of going to the right, I'm taking it back out. So how would you say this sentence, which is equivalent to everybody doesn't like something?
So it's not true that someone likes everything.
Okay, yeah. It is not true. It is not the case that someone likes everything. Another way of saying it is nobody likes everything. It's not the case that there exists a person, how about this? Nobody likes everything. Actually, so. Those are equivalent, logically. So, somebody comes in and says, I've got a sales pitch for, how about, nobody likes everything. And that's what I said, well, how about we just say everybody doesn't like something? Maybe there's some reason, it's.
I think nobody likes everything. It's cheaper.
Nobody likes everything? Yeah, it takes less app space, right? You take less ink, but everybody doesn't like something. But then the other half was, but nobody doesn't like Sara Lee. So that's the next thing I'm going to do. How about that? So it's everybody doesn't like something, but nobody doesn't like Sara Lee. So what is a logically equivalent way to say nobody doesn't like Sara Lee?
Everybody likes everything.
So
Is that the same as saying everybody likes Sara Lee? You think? Well, let's prove it. Okay. There does not exist a person, so that's my. It is not the case that there exists a person, X, such that so nobody doesn't like Sara Lee. So it is not the case that X likes Sara Lee. So you see, it's like a double negative, like nobody and doesn't. There's a double negative going on there, and you see the double negatives. It is not the case that somebody doesn't like Sara Lee. That's why, another way of saying it, nobody doesn't like Sara Lee. Nobody means there does not exist a person. That person doesn't like Sara Lee. It is not the case that X likes Sara Lee. So let's take this negation inside. And the negation of negation, they cancel out, right? So if I do, for every X in U, it is not the case that X likes Sara Lee, but the negation and this negation cancel. So it's really equivalent to saying X likes Sara Lee. So what we're really saying is that for every person X likes Sara Lee. So logically, we're equivalent to saying everybody likes Sara Lee. What do you like better? Everybody doesn't like something, but nobody doesn't like Sara Lee. Or you say, nobody likes everything, but everybody likes Sara Lee. I don't know. They're equivalent. They're logically equivalent. But I like this original slogan better.
So
It's nostalgic, I guess.
concatenate the sentences together, would we have to rewrite the whole?
Well, this is a but,
So it's not there.
so it would be an and, you know. I mean, it's if I negated the whole. No, I'm not negating the sentence. I'm just. This is still an and. I haven't negated the slogan. I just translated it into logical, you know. So it's, I would still say nobody likes everything. I would still probably say, but everybody likes Sarah Lee. Nobody likes everything, but everybody likes Sarah Lee. It's just more confusing, it seems like. But it's equivalent to saying everybody doesn't like something, but nobody doesn't like Sarah Lee. And then people mistakenly thought that said nobody does it like Sarah Lee, like they're the best at making snack cakes or whatever. But you guys like the joy of eating now better? Joy of eating. Okay. So you notice in the homework section they have all these kind of silly phrases, silly sentences that they want you to translate into logic, like I won't eat it, or I don't eat anything that has a face, or something like that. You guys haven't seen those questions? No? So in other words, there does not exist something with a face that I would. So it's like that. So somebody had a hand raised?
Yeah, you did, but,
Sorry.
no, it's okay. I was with, there exists an X, or exists an integer X
Mm-hmm.
for every Y integer, whatever.
There's this integer x such that for every integer y,
Yeah, X plus Y equals 0. And when we took that down to the bottom, it was X plus Y does
Yeah,
not
so-
equal 0, but it's
so this one was false. This is what I started with. It was false.
Yeah.
So then I took the negation of it and I said that's true.
and you have to put the negation by the,
And I just toggle it through here and yeah.
but, in that case, isn't it also true that X plus Y does equal 0?
So for every integer x, there exists an integer y such that x plus y does not equal 0. So I agree with you said that if I change it to an equal sign, that is also a true statement. But it just doesn't happen to be the negation of the statement I started with. Okay. Yeah. Yeah, I think we had a sentence like that too. Like, you know, if this is a true statement, but so if I change this to an equal sign, it's still a true statement. It's just not the logical negation of the original statement that I started with. Okay. All right. So part of your homework you just turned in, you remember proving. This was 2.6, number 12, that we proved that the negation of P implies Q is equivalent to P and not Q. You showed that by the truth tables, right? You showed that truth tables were equivalent. Okay. All right. So think about this. What we're saying is that it is not the case that P implies Q. Well, when can P implies Q be false? It's only false when P is true and Q is false. So therefore not Q is true. So you see why, again, even without doing truth tables, that these two statements are equal. If we're saying it is not the case that P implies Q, that must mean that P is true and Q is false. So that's saying that P is true and not Q is true. Okay. So why am I saying this? Well, because if I want to take the negation of a conditional statement, I can rephrase it like this. Instead of saying it is not the case that P implies Q, I can say P and not Q. I'm going to give you an example. How about
So would P implies Q be the same as not P and Q?
what you're saying? So if not P or Q, what I say? Sorry, if I said you said it.
Yeah,
Sorry,
basically.
ask your question again.
It said P implies Q
P implies
equal
Q.
to not P and Q.
Equal to not P and Q. That's what you're saying?
Yeah, basically take, or wait, no, that would be, have to be a not P or Q.
Yeah.
Whatever.
So this is true when the first statement is false, or when Q is true, then this P implies Q will always be true. And so if you took the negation of this would equal the negation of this. By De Morgan's law, that would be P and not Q. Okay. So we got it right. This P implies Q does equal not P or Q. All right. So not the negation of P implies Q is equivalent to P and not Q. So here's the statement. All right. For every integer x is prime implies x is odd. So for every integer x, if x is prime, then x is odd. Another way of saying that. So what I'm really saying is every prime number is odd. That's one way of translating this to English. Is it true that every prime number is odd? No. So this is a false statement. Okay, so let's take the negation of this. So I'm just going to rewrite it with the negation symbol. Okay, so then this must be true if I negate the false statement. And let's rework this. So it is not the case that for every integer x, x is prime implies x is odd. So when I bring this in, I'm going to get there exists an integer x such that it is not the case that x is prime implies x is odd. But we just said that the negation of P implies Q is equivalent to P and not Q. So let me rewrite that. There exists an integer x such that, so not P, I'm sorry, P, so I'll rewrite this, P and then the negation of Q. So there exists an integer x such that x is prime and what? So this is P and not Q. Yeah, the negation of x is odd. What's a better way to say it is not true that x is odd? X is even. Let's say that, since we're talking about integers. So this statement is the negation of the original one. So there exists an integer x such that x is prime and x is even. Okay. So every prime number is odd. That's false because there's an integer that's prime and even. Right? There's a prime number that is also even. Another way of thinking of it. Okay. So saying that it is not the case that x is prime implies x is odd, the same as saying there is an x that is prime and even. How about more examples of this? All if a function is rational, then it is a polynomial.
I think that was
Yeah, it's something related to a homework problem. So a rational function, by definition, is a polynomial divided by a polynomial. Okay, so think about that. So if a function, if it looks like a polynomial divided by a polynomial, does that make it a polynomial? X plus 1, polynomial. X plus 2 is a polynomial. If I define a function like this is a rational function. Is this function a polynomial function? No. This does not look like just the thing that's on the top or just the thing that's on the bottom. It's not like powers of x's, adding powers of x's. So this is a rational function, but it's not a polynomial. So the original statement, this is actually a false statement. Okay, if you think back, when I say an if-then statement like this, it's really a universal statement. We're saying for every function, if that function is rational, then that function is a polynomial. Okay, so it's really a for all functions. Okay, so for all functions, if a function is rational, then it's a polynomial. That's false. Okay, so the negation. Okay, for every function, for all functions, if a function is rational, then it's polynomial. So I'm not going to translate it into symbols and then negate it and everything. So think about it. A for all statement, the negation of a for all statement is a there exists statement.
You forgot to move the camera.
So, some functions are rational?
Okay, so we said for all functions, if a function is rational, then it's a polynomial. That's a false statement. So the negation of this sentence is a for all statement. So the negation would be a there exists statement. So I proved it with an example. There exists a function that is rational and not a polynomial. That's P and not Q. Okay? So there is a polynomial, there is a function that is rational and not a polynomial. So that's the negation would be true. And I gave an example, f of x equals x plus 1 divided by x plus 2. Here is a function that is rational and is not a polynomial. Okay. So if a function is rational, then it's a polynomial. The negation would be there is a function that is rational and not a polynomial. If P then Q, this is P and not Q. Okay? Any questions? One more. Okay, so we're going to assume we're talking about for all integers x. Okay? If x is divisible by 4, then x is divisible by 8. If x is divisible by 4, then x is divisible by 8. True or false? It's false. So maybe in your mind you're convincing yourself this is false. Now how would you do that? Well, you'd find a number that's divisible by 4 and not divisible by 8.
X equals 4.
4. Yeah, 4 is divisible by 4, and 4 is not divisible by 8. 12. 12 is divisible by 4. 12 is not divisible by 8. So that's how you would prove this is a false statement, right? So the negation so there exists an integer z. I might just write it out. There is an integer. I kind of want to just keep the English there. There's an integer that is divisible by 4 and not divisible by 8. That's a true statement. Any questions? Teresa.
When we are writing them, I'm not gonna ask the question. Just whenever we see an if then, do we know to write it P and not Q?
You know, I mean, that's one way to write the negation. You know, you could just say it is not the case that if x is divisible by 4, then x is divisible by 8. That's a negation. But that's not as useful as saying there is an integer that's divisible by 4 and not divisible by 8. That's often how you prove a statement is false. If I wanted to prove this was false, what would I do? Well, I'd find a number that's divisible by 4 and not divisible by 8. So that's why it's nice to know that that's the form of the negation. That's an equivalent form of the negation. Okay? All right. That is all I'm doing from 2.10. Now I did not assign a homework problem because I wanted to give you guys time. We got plenty of time here to look at the problems from chapter 2. Now, very few of you have this book with you, right? Is that right? Okay, so I can pull up the book here on the computer real quick. But a couple of things just to wrap up chapter 2. If you want to, if you get an idea to read 2.11 and 2.12, but there are no problems in it. It's more like it's kind of interesting. This guy there's a kind of like a little section to kind of address some. Instead of having like narration or some kind of aside in his book, he puts a new section in to give like a note to the reader. So 2.11 talks about logical inferences, which is very important when we make in mathematics. You know, if I say if P then Q, say I know this is a true statement. Okay. Well then, if I can show P is true, then I can therefore make the logical inference. I can assume then that Q is also true. Okay, so that's kind of the stuff that we're going to use when we write proofs. I mean, when you think about math logically, so that's it. They talked about that in 2.11, and then 2.12 it talks about 3 reasons why we study logic. Okay, so I tried to convey those reasons as we're going through this chapter 2. But one reason he gives is if you can write a sentence in symbolic logic, you have to know exactly. It forces you to know exactly what the statement is saying. Okay, so that's one reason. If you're going to prove a statement is true, if you can rewrite it symbolically, you know exactly what it's saying. Secondly, he says by using this logical inferences, you can produce new information. You know, you can have two statements. And if you know they're true, then you can infer another new information is true. And then third, we'll use this when we do, for example, proofs by contrapositive. It's often useful to change a statement to a more useful equivalent statement. Like, you know, like I said here, there's a function that is rational and not a polynomial. Or, sorry. If a function is rational, then it is polynomial. I could just say it is not the case that a function is rational, then it is polynomial. It's more useful to say that maybe there is a function that is rational and not a polynomial. Or it is not the case that if x is divisible by 4, then x is divisible by 8. A more useful phrase might be, there is an integer that is divisible by 4 and not divisible by 8. So that's an example of how you use an equivalent, potentially more useful statement. So you can do that using logic. So those are kind of wraps up chapter 2. So right now,